Marcos Jardim from University of Campinas, who will talk about logarithmic tangent shifts on projective varieties.
Yeah, so first I'd like to thank Carolina and Ana Maria for inviting me for this meeting and for bringing everybody together in this wonderful place. I was going to talk about something complicated on instantons and derived categories and bridgeland stability, but then I decided to change for this topic, which is more elementary, and hopefully there will be something for everyone here. And this is a series of papers that I've done with these collaborators. The most recent one with William Montoya just got to the archive today, and there's ongoing work with Alan Muniz and Mauricio Correa continuing these efforts. So I have just a few slides. I'll mostly use the board, but just a small outline of the talk. I'll start talking about the classical theory of free divisors. That it's actually very beautiful theory between algebraic geometry and commutative algebra that maybe not everybody is familiar with. And then I'll discuss two versions / generalizations of this classical theory, which is the stuff we've been working on recently. So just to start with this classical theory, and I'm not going to be able to hold everything at the same time. So the classical theory starts with a polynomial. So let's take f. Doesn't have to be C. A polynomial in n+1 variables, homogeneous, degree D. Then we can do the following. We can think of the partial derivatives as a morphism of sheaves to, right, so these are all the partial derivatives for f, and look at the kernel of this that I'm going to call Tf. Right, so this Tf will be the kernel of this morphism, and this is always a reflexive sheaf. Meaning that Tf is always isomorphic to its double dual as a sheaf. And sometimes it's locally free. For instance, when the divisor that we call D, 0 of f is a divisor, when this divisor is a normal crossing divisor, then this Tf is locally free. And what Saito noticed is that it can be free. It can be split as a sum of line bundles. And these special type of divisors are called free. So D is called a free divisor if Tf splits as a sum of line bundles. And free divisors are very special. For instance, a smooth divisor is never free, and typically free divisors have to be very singular. So if your divisor has only mild singularities, most likely it won't be free. And one of the things Saito did, so maybe before Saito, let me talk about the interpretation of this. Sections of this bundle are the syzygies for this matrix. So you can think of this as a 1 by n+1 matrix. Right? Have one line and n+1 columns. And sections here are syzygies, right? So every time you have a section, say take a section of degree E of Tf, this can be represented by some map eta or mu, into these n+1 copies of OPN1. Right? And of course, the composition here, with the nabla F will be 0. Right? So these are vectors that are syzygies for this matrix. Right? So this can be thought as the sheaf of syzygies. Sheaf of syzygies for this matrix. Right. Okay, and it also has some nice relation with a singularity theory, because if you look at what is the image of this map, it's going to be some ideal sheaf twisted by D. This J is the so-called Jacobian ideal, Jacobian scheme. And it picks up the singularities of the divisor capital D. Right? So this sheaf, in this case, can also be characterized as the sheaf of vector fields that are parallel to the divisor at the points of the divisor. So if you look at this other diagram here, where this is the Euler map, right? So the multiplication by the coordinates into n+1 O1. And I'm going to omit the Pn here. Here we have the nabla J into the ideal. This map, if you look at the composition of these two maps by the Euler formula, this is just going to be the degree of f times f again. So just that map is just multiplication by f in some sense, which means that the kernel here factors through the co-kernel of this map, which is just the tangent bundle. Okay, so this is just the tangent bundle of Pn. And what you get here, the co-kernel of this map, will be the ideal of the Jacobian scheme as a sub-scheme of the divisor. Right, so and this sheaf here also appears in some other contexts. This is the so-called log tangent sheaf. In this context, this is the log tangent sheaf, which is usually defined as follows. You take on any variety x, say x some smooth projective variety, you can start with the tangent bundle over x, tx, and then you have the restriction of tx to the divisor, and that maps onto the normal bundle of the divisor in x, better known as ODD in this context, or ODD, capital D. Maybe I should say that D is some divisor, some reduced divisor. So all my divisors are reduced. Some reduced divisor here, so you can look at this composition, and the kernel of this, and the kernel, it's what is called the logarithmic tangent sheaf. It's here in the corner, so maybe I should write TXD. And as you can see, this sheaf are the vector fields, right? The vector fields that are parallel, right? So there are not, that when you restrict to this normal, they vanish. So they are the vector fields that are parallel to the divisor on the points of the divisor, right? So the sections are vector fields defined everywhere in X, but at the point of the divisors, they are just parallel to the divisors. Okay? So this sheaf of syzygies coincide with this log tangent sheaf. And Saito, in the 1980s, came up with a very nice criteria to decide freeness. Saito criterion. Which is the following. Say you have n1 up to eta 1 up to eta n syzygies for nabla f, right? So given some divisor, look for n syzygies for nabla f. Now, we know that the divisor is free. Well, the Saito criteria says that divisor is free if and only if the determinant of the matrix made up with these guys, right? So remember, each of these etas is a collection of n plus 1 homogeneous polynomials of degree, in this case of degree, what, e minus 1 or e plus 1. So you have this, you just make these vectors into columns of a matrix plus this Euler matrix, this Euler map here, which is just all the coordinates. And if this determinant is a multiple of f, the original f that you started with, your divisor is free, and these guys are exactly a basis for the module of syzygies, or yeah. So for some choice of syzygies, choose any syzygies that satisfy this. Now, if they satisfy this, then they are a basis, and your module is free. And this lambda is some non-zero scalar. And here, for this to work, I also have to assume that the characteristic of the field does not divide the degree of the polynomial, right? Because I need the Euler formula. I need this here. So I need the Euler formula. Okay. And usually I don't do proofs in talks like this, but this proof is so easy and that I can do here. Maybe I'll erase this bit. And I'm a big fan of commutative diagrams, and the proof here is just a commutative diagram. The idea is as follows. Let me do the proof here. Let me say that f is just a sum of some O minus ek, n of these, right? And these syzygies, they will be regarded as maps from O minus ek to n plus 1 copies of O1. Okay. With this in mind, I can make this, I put this in the wrong position. With this, I can make the following diagram. I take this F, this free sheaf plus O. Then I make this matrix M here. Let me call this matrix M. Going to n plus 1 O1. Then, since this first bit are syzygies, the F summoned will map onto the kernel of the nabla F. And this O will map here, just like there, and this is DF. Right, so you have these short exact sequences here. And then the snake lemma will give you that, let me call this map theta. So you go from the co-kernel of theta to the co-kernel of this matrix M, and then this other co-kernel here. Well, this co-kernel, we know what it is, right? So it's the ideal of J as a subscheme of D. Now, this thing here is supported at F. This is supported at D, right? So the support is V of F. And the support of this thing is V of the determinant. The support of this sheaf is V of the determinant of the matrix M. So if the two things coincide, right? So if the determinant is the same as F, these two supports will coincide, and this guy will be supported in codimension 2. But then you have two guys here, two reflexive sheaves, and this is the co-kernel should be supported in codimension 1. So this condition here, right? The fact that these supports are equal essentially imply that theta is an isomorphism. Okay, and so this was essentially proved by Saito in the 1980s, and since then, in the past 40 years, there is an enormous amount of literature in algebraic geometry and commutative algebra. Maybe I should give an example, right? How to apply this. Very simple example. It could be instructive later on. Let's take on P2. Let's take on P2 just an arrangement of lines, all lines passing through the same point. Right? So this inside P2, a bunch of lines passing through the same point. So this means that F actually depends only on the two first coordinates. Right? So this is a cone, right? So it only depends on x0 and x1. Does it depend on x2? Right? So you have two very easy syzygies. One syzygy is something like 0, 0, 1. Right? So nabla F would be the derivative with respect to 0 and 1 and then 0. Right? So you have just this is going to be a syzygy, and also D1F minus D0F. It's going to be another syzygy for that. Right? And then you put the coordinates here. Right? Compute the determinant of that. This is just degree of F times F. Right? So it's just this determinant here, and the Euler formula gives you that this is degree of F times F. So one very simple example to satisfy this. And also gives me an excuse to talk about the Terral conjecture. Terral conjecture is about line arrangements. So it's the situation where this F is just a multiple of a bunch of polynomials of degree 1. Right? So you have a bunch of, the divisor will be a bunch of lines in P2. And Terral conjecture says that suppose you have two line arrangements with the same combinatorics. So with the same intersections between lines and the same number of lines and the same number of intersections with the same multiplicities. Right? So if you draw the incidence diagram of these intersecting lines, the diagrams are equal. That's what I mean by the same combinatorics. this, or I don't know what a matroid is, but I'm ready to trust you. Right, so if you have two arrangements with the same matroid, right, then if one is free, if and only if the other one is free as well, right? So freedom is determined by the combinatorics, not particularly in the way the lines are the particular set of lines, but just the way they intersect one another. That's Terau's conjecture. And also gives me an excuse to say it's easy to see how this simple example generalizes. So whenever you have a cone, right, like this, some polynomial that doesn't depend on one of the variables, a cone over a free divisor in smaller dimension, is always free. Right? So a cone of a free divisor is always free. So I was first exposed to this theory some, I don't know, maybe 5 or 6 years ago. Together with Daniele and Jean, we wondered, okay, so how do we generalize this for more polynomials, right? So instead of considering one polynomial, consider more polynomials. That's the item 2 there, the several polynomials, right? Or in other words, instead of looking at divisors, look at subschemes of higher codimension. And what about other varieties, right? Because the definition of the tangent sheaf, the log tangent sheaf, works for any variety, as I explained in the corner here, right? So the log tangent sheaf, and this is, there are several notations for this, but this is a notation that Daniele likes because it's in a book by Cernesi, I think. So this is the, not a surjective map, but a map onto ODD. Right. So this is defined on every X. Okay. So can we generalize and find cytocriterions and find examples of free divisors on more general X's? Right. So that's the motivating questions for part 2 and 3. Okay. When this sheaf is locally free? Well, in particular, when it's a normal crossing divisor, it's always locally free, for instance. But more general, yeah, more generally than that. Yeah. So the point is that the Jacobian scheme has to have codimension exactly 2. Right? So if the co-kernel of this map has codimension exactly 2, then it's, if and only if it's locally free. That's the criterion. So something like your divisor on a threefold has to have only one-dimensional singularities. Cannot have isolated zero-dimensional singularities. Okay, so let's get started on part 2. I forgot this bit here. Part 2. So the idea now is that we take a sequence of polynomials, f1, fk, such that the GCD of sigma is just 1, essentially. Right? So if they have a common factor, just eliminate the common factor. And also I'm going to assume that they are algebraically independent. Meaning that there's no polynomial that applies to these k polynomials that give you 0. That's algebraic independence. Turns out that algebraic independence is equivalent to saying that you can, well, before I had one polynomial and I took the partial derivatives of that, so they are all homogeneous polynomials. Homogeneous polynomials on n variables, and the degree I'm going to denote by d1, dk. So you can now put all the gradients together in a single matrix. This now goes into the O of the di's, like this, right? So this is a K by n plus 1 matrix. And look at the kernel of that. So this is what we call the log tangent sheaf for my collection of polynomial sigma. Simple enough. This, again, this is always reflexive. Sometimes locally free when, maybe I can write it since you asked, so it's locally free if and only if if you look at the common zeros of the maximal minors, the K minors of this, right? So the maximal minors of this matrix, and this has pure codimension 2, right? So this is the condition for local freeness, and sometimes it's free. Sometimes it splits. Splits. And I'm saying, when I say splits, I mean splits as a sum of line bundles. It's totally decomposable. Okay? So this is my definition of freeness. Now, I'm going to say that sigma is free if and only if this T sigma splits as a sum of line bundles. And one observation is that this sheaf here, T sigma, in general, they really depend on the polynomials, not only on the ideal given by these polynomials. Yes? No, it doesn't have to be a regular sequence, just algebraically independent polynomials. It's a bit weaker. It's weaker. It can be a regular sequence, but it doesn't have to be. Yes, if it's a regular sequence, then it's algebraically independent. Yeah.
Can you do the Kelly trick?
I don't know, I haven't tried. More questions? Good. So the fact that it's algebraically independent, so the algebraic independence is equivalent, in fact, to say that the rank of TF is the maximal rank. So it's precisely n plus 1 minus k. Right? So this is how algebraic independence matters to us, because then it sort of fixes the rank of this kernel. As for a geometric interpretation, you can see that, so this is again the syzygies for not only one polynomial, but the syzygies for this entire matrix, right? So this is the sheaf of syzygies for this matrix, which means that it's an intersection of all the syzygies for each of the polynomials separately, right? So the T sigma it's an intersection of all the TFIs, right? And then you can show that this T sigma is also a subsheaf of the log sheaf for C. I should say what C is. Let me say C is the common zeros of sigma. So this is a sheaf that it's defined by Cernesi similarly to what was done before. So this is the kernel of this map from Tx to Tx modded out by restricted to C, and then you take the normal bundle, the normal of C in X. Right? So it's the kernel of this composition is how this thing here is defined. Right? This sheaf is in Cernesi's book. This sheaf governs the deformation theory for C inside X. The problem is that this sheaf here is it's never locally free, right? I think it can be reflexive, well, never locally free when C has codimension higher than 1, right? Then this is never locally free when C has codimension at least 2. Let me see. And I guess it's not even reflexive, but I'm not so sure, so let me not state that. So never locally free. When codim of C is at least 2. But this sheaf can then be regarded as some sort of nice part of this other sheaf here, right? Because it can be free, it can be generated by some syzygies and so on. So this is some sort of nice part that will give you in some, let me not say more about this. Take one of these guys here. Yeah. So this is one motivation to study, and this is never an isomorphism, right? So for one thing, because of the rank. So this guy here always has rank n. Right? While this we've seen has rank smaller than n. Right? So this is never an isomorphism, and this T sigma is sort of a nice bit inside of that paper. So one of the things we do with this in our paper is, for instance, we do a classification of the pencils of quadrics. So by that we mean when you have two polynomials of degree 2 on n+1 variables, and this is a list of all the free pairs of polynomials. So they only, I want this, yeah. So this n hat here says that every free pencil of quadrics in Pn is sort of a pullback from lower dimension, right? So dimension 3, 2, or 1. In other words, depend on 4, 3, or only 2 variables. This column here of the exponents say what are the, because when it's free, it splits as a sum of line bundles. Oh no, it's this one. It splits as a sum of line bundles. So this case here means that it's n minus 3 copies of O plus 2 copies of minus 1, this case here, right? So n plus 3 copies of O, 2 copies of minus 1 again, and so on. Right? So these are the sort of the splitting type of the log tangent sheaf, and this is a classification up to change of variables of all the free pencils of quadrics. So this is one of the results of our paper. Another nice result is that if before this sheaf was coincided with the log tangent sheaf, now it can also be regarded as the tangent sheaf of a foliation on Pn. Right? So the diagram now is like this. So we have the T sigma inside TPN, and let me call M sigma. So this M sigma will just be the image of the nabla sigma. It's some torsion-free sheaf, some torsion-free subsheaf of this split sheaf here. Oops, sorry, I'm skipping one step here. N plus 1 or 1. So this is the M sigma, this is the nabla sigma. And again, we do the same trick as before. So this is the Euler map multiplication by the coordinates, which composes with this and gives you a map, actually a map here, which can be described as follows. It's just a degree of 1 times F1, degree of k times Fk. Right? So this is actually a map from O to this split sheaf, right? But then it factors through the image of nabla, right? Because it comes from this, so it factors through the image. So I'm going to write it in this way just to simplify a little bit. And then again, the tangent sheaf of Pn appears here. And we get some quotient that I'm going to denote by N sigma. And this is the T sigma here. Okay. So this sequence now, because this condition that the GCD of sigma is in K star means that this guy is torsion-free, this N sigma is torsion-free. So this sequence that I highlighted here defines a distribution of codimension, what it is again, N minus K on Pn. N minus K, codimension N minus K on Pn. And then one can show that this distribution is actually integrable. So this is, the integrability in general was done by Muniz in an appendix of our paper. So this is always a foliation on N sigma. So before this guy was the geometric interpretation was the tangent log sheaf. Now it's the tangent sheaf of some foliation when k is larger than 2. And this led us to find a very nice example on P3 again. So if you take this pencil of cubic surfaces, actually a pencil or two cubic hypersurfaces on P3, the only two non-normal cubic hypersurfaces, because they are singular along the line, both are singular along the line x0, x1. So if you run this game with those two polynomials, you find a foliation whose tangent sheaf is the no correlation bundle twisted by -2. Right? So never mind too much what the no correlation bundle is, just that it is not split. Right? It's a locally free sheaf that doesn't split as a sum of line bundles. And this gives a negative answer to a conjecture by these guys that these guys made in the 90s or something. So their conjecture was that if you have a codimension 1 foliation, a rational foliation on P3, a codimension 1 rational foliation on P3, then the tangent sheaf always splits as a sum of line bundles. So this was an example that disproves that conjecture. So that was, we were very happy about that. And also, we managed to find a version of the Saito criteria that also applies to this situation. And what I'm stating there is actually what I call the mother of all cytocriterions. Yeah, I guess I have a... and it's very similar to just twinkling with the proof that I gave you. Yeah, this button, right? No, it's this button. Yeah. So instead of having a free sheaf, as I did in the example here on the board, you can take any sheaf F, any reflexive sheaf F, right? And G, just some any other reflexive sheaf as well. Right? And you find two maps that I'm calling theta and gamma onto O. Yeah, so here the notation is slightly different, but the idea is the same, right? Just put a 1 here in this OPN. So you get this matrix, this map into these R copies of, and this R can be any R. In particular, can be n plus 1. Right? And some matrix onto some split sheaves like this. Okay. Call the Tm the kernel of this matrix M, right, with this property, right? So this theta is like a syzygies for M, and the gamma is just anything that composes to some mu that is injective. The important thing is that this mu is injective. Then, if some combination of GCDs of the maximal minors of these matrices coincide, then this map here, this induced map from F to the theta sigma is actually an isomorphism. Right? So this is, the cytocriteria is sort of a special case of this one, and with a theorem like that, we can produce more examples. Let me give you one very simple example. Here on the board. Let's take two polynomials, f that only depends on two variables, right, and some other polynomial g that depends on the other two variables. Right? Everybody on P3. Okay? So then the nabla sigma, so sigma will be this pair here. So the nabla sigma will look something like this. And then you have two obvious syzygies, right? You can replace, you can switch and change sign here, switch and change sign. You have two obvious syzygies. And then that matrix M, so this would play the role of the matrix M there. The matrix theta for the syzygies would look like this, D1F minus D0F. And so this is the theta there on the slide. And then the other, you just put x0, x1, 0, 0, x2, x3 here, 0, 0. This is the matrix gamma. So if you look at what is gamma composed with the other way around, right? So nabla F composed with gamma, this is just going to be degree of F times F and degree of G times G. Okay. So this is an injective map. And if you do that computation, so the M now is a square matrix, so that GCG is just the determinant of the matrix. And the determinant of the matrix, this means the determinant of M That thing over there means the GCD of M composed with gamma, which is that map mu. Oh yeah, so this, I wrote it like this, but it's a 2 by 2 matrix in this case, right? So it's 0, 0, deg G times G, right? So this term here is just 1, this GCD. This is the determinant of the matrix. The determinant of the matrix is just degree of F times F, degree of G times G, multiplying everybody. And this is just the degree coincides with the determinant of that other matrix there. Right? So apply that theorem to this situation, maybe thinking a bit while you're not hungry and crazy to go to lunch, and you get that this is, any such pair is always free. There's another application of this map, of the theorem that was in the previous slide, which is, goes like this, right? So, oh no, so sorry. So this is already the toric varieties. Okay, so go back. Let me see how I am for time. Yeah, maybe I've got another 5 minutes to talk about the toric varieties. And this is the first time in my life that I'm presenting something on toric varieties, so please be kind. I really don't know much about toric varieties. But by now, you can imagine what I'm going to say, right? So it's, there's a more or less easy way to transport this setup to toric varieties, which is the following. So let's say X is a simplicial toric variety. So over some fan sigma. And we've, the Cox ring, I'm going to denote by C X1, XR. Or maybe I start with yeah, X1, XR. Or maybe I start with 0, I don't know. And then take some homogeneous polynomial here. This homogeneous polynomial will define you a divisor on the toric variety. And with that, I can take derivatives. Right? But now these derivatives will go from what Antonio yesterday called the Cox sheaf. Where these divisors are the zeros of the xi, so I guess I start with 1 here. And then you just take the derivative of these homogeneous polynomials, and it will land you on OX beta, where beta here is the degree of f, which is, as I understand now, is an element of the class group of X. And then you take the kernel of this guy, and that's our, again, our TF that we call the toric log tangent sheaf. And then in the paper that appeared today, we do, a version of the Saito criteria. A version of the Saito criterion for toric varieties. Never mind too much what it is. We also explain how this is related with the usual logarithmic tangent sheaf. It's the same theme, right? So you take some syzygies, form some matrix, and if this determinant of this matrix coincides with F, then you get that this sheaf is free. By the way, I didn't tell you what it means for a sheaf to be free, right, in this context. Right? We say TF is free. So F is free if TF splits, generally not as a sum of line bundles, but as a sum of rank 1 reflexive sheaves. This is our concept of free in this context. So you have a version of that cytocriteria for this situation. Let me explain what is the relation with the usual log tangent sheaf. Relation with usual is given by a short exact sequence, which is OX. So this is the Picard rank minus 1. Will always be a sub of this TF, and the quotient is precisely the log tangent sheaf for the divisor D. So this is some sort of extension of the usual log sheaf by these trivial bundles. And then we can do various examples of free sheaves. For instance, any torus invariant divisor D is, then TF is free, right? So D invariant is always free. Note that there are two distinct concepts here. One is the freedom of this guy. So this guy is a sum of rank 1 reflexive sheaves, and the other thing is the freedom of this guy. And they are in general different, right? So one can be free without the other being free as well. But so any invariant divisor is always free. Cones over free is also free. So cone over free is free. One other example is the so-called braid arrangement. So the braid arrangement is made up like that. You put together all the generators of the Cox ring that have the same degree, right? So X1 up to XR1 all have the same degree in the class group, and then the L2 all have some other degree in the class group, and so on. Right? And then you take all the differences, all the differences that make sense. Right? So, I'm pressing the wrong button. Yeah, okay. So these are all the product of all the differences that make sense, so that Xi and Xj have the same degree. Right? So this is what we call the braid arrangement. It generalizes this notion of the braid arrangement on Pn, in which you take all the differences of all the variables, because all the variables have degree 1. Right? So that's a hyperplane arrangement on Pn. Here it's going to be some complicated divisorial arrangement on the variety. And this braid arrangement, you can use our cytocriteria, and this is also free. Right? Yeah. Yes. Yeah, except for hyperplanes. Yeah, sorry. Hyperplanes are the only smooth free divisors, which it gives you an important lesson for life, right? So you're either free or you are straight, right? So if you want to be straight, you're never gonna, if you want to be straight, it's the only way to be free and smooth. Yeah, that's it, right? So the only way to be free and smooth is to be straight, right? Otherwise, you gotta have some singularity if you want to be free. So yeah, so TF is maybe free while the other one is not. And I have one example to finish. Maybe I won't do the whole calculation, but just say what the example is to illustrate this point that one thing can be free while the other is not. So let me take X to be the projectivization of a bunch of line bundles on P1. So let's take this toric variety. So the Cox ring of this, I'm going to write as xy for the coordinates here, and then u1 up to un for the fibers. The Picard is 2, right? So it's z times h, which is the relative hyperplane section, and z times f, which are the classes of the fibers. Right? So these are the hyperplane, the relative hyperplane and the fibers. Now I want to take f just depending on x and y, right? So, so that the corresponding divisor is just a union of lines. Just a union of fibers, sorry. Just a union of fibers. So this is in particular a cone, right? So a cone over P1, anything on P1 is always free. So we know from general theory that this is free. In fact, TF is split as n copies of OXH plus OX 2 minus DF, right? So this is the TF in this situation. And then this sequence here D is the number of lines here, the degree of this polynomial or the number of lines in this arrangement. Right? So I'm saying lines because I don't know why, the number of fibers. Right? And if you look at this sequence here, it would be OX inside this TF. And this guy here, there are two possibilities, right? So, well, when, let me put here, so when K or D is at least 3, right? Then you don't have any maps from OX to this summit here, right? Because there are no sections. If D has at least 3, this is going to be negative, and OX doesn't map here, so that map has to fall into this N guys here. Right? So the co-kernel will have this summand plus the relative tangent. So it will be OX 2 minus D F plus the relative tangent bundle here. And this is when D is at least 3. Okay. If in addition we are looking at n equals 2, so that this is a surface, so this becomes a Hirzebruch surface, then this relative tangent sheaf is actually just a line bundle. Right? So we get that the T, and this is, in general, this will be the log sheaf. So this is the TXD. Right? So when x equals 2, we get that the logarithmic tangent sheaf for this union of fibers will be just OX 2 minus d, f, plus this guy here, which is OX 2H minus AF. Right, so A here would be A1 plus A2 in the notation over there. Okay. So this is just a neat example in which we use this theory to the toric version of Saito's theory to give to describe one or several families of free divisors on varieties that are not just a projective space. Thank you.